computer. All right.
Okay. So this is the first talk. I'm going to give a survey on intrinsic flexibility of the positive mass theorem. Some people like Dan will probably be better at answering questions about precise asymptotic flatnesses and details of that sort. I tend to be very geometric and somewhat vague on points of that sort. So that's why I made sure Dan was here. Anyway, so let's just get started. That's just a picture from my paper with Dan years ago. So we assume that M3 is asymptotically flat with scalar greater than or equal to 0. So asymptotically flat roughly means that in these pictures, all of these manifolds are asymptotically flat, and the asymptotic flatness is talking about how it's behaving out here, almost like asymptotically like Euclidean space. So there's a specific formula about how quickly the metric tensor has to decay at infinity, and usually it involves both the metric tensor itself, its first and second derivatives, how quickly they have to decay. We always assume that these manifolds all have scalar greater than to 0. In my talk, I'm going to stick with 3 dimensions for simplicity, although some of the results are true in higher dimensions, like, for example, the positive mass theorem itself. The Shane-Yao positive mass theorem says that the ADM mass of a manifold, which is asymptotically flat with non-negative scalar curvature, is greater or equal to 0. The ADM mass is sort of measuring the decay out here. I will give more about that in the next few slides. And if the ADM mass is equal to 0, that's true if and only if M3 is actually flat Euclidean space, which I've depicted here as a flat disk. So as a general rule, in all of my pictures, I'm drawing 2-dimensional things, surfaces, to represent 3-dimensional spaces. So when you see things like this well here, this is a sphere, that would be an S2. And this would be a ball in Euclidean space that's become deep and narrow. So just so you have a sense of what my pictures are trying to depict here. Penrose proves that if the boundary of M3 is what's called outermost minimizing, which is something I will discuss later. So if the manifold actually has a boundary, that happens in these pictures here. I can draw the boundaries in red. So if they actually have a boundary, and that boundary is what's called outermost minimizing, which I will explain in the next slides, then the ADM mass is bigger than 0. In fact, it's bigger than or equal to a formula depending on the area of this boundary, which I will give in detail later. That's the Penrose inequality. And the key open question that's a big discussion this week is if MJ3 are as above, which means that they are asymptotically flat. When I say as above here, I mean that they're asymptotically flat, they have the scalar non-negative, and if they have a boundary, it's outermost minimizing, and otherwise we'll actually forbid, if it doesn't have a boundary, then we'll assume that there aren't even any minimal surfaces at all. And we say if MJ3 are like this and have the ADM mass going to 0, does the manifold converge to Euclidean space? So what we have here in the picture here, this is from my paper with Dan Lee, this image, is we looked at these sequences of manifolds. So what you want to do is say, oh, I'm thinking about this manifold and then this manifold. This one, the ADM mass is going to 0 if it's sort of like becoming flatter at infinity. The non-negative scalar does allow for these kinds of negative curvatures that are happening here, but there's an entire S2 bending inward. So it still has non-negative scalar curvature, even though there is this thing, which I usually will refer to as a well, a gravity well around a planet. And in this particular example on the left, we basically have smooth convergence of the sequence to Euclidean space. Here we have examples with this outermost minimizing surfaces. So these are basically black holes. So you can't cross this horizon. So we only look at the part outside. So this part outside is called the exterior of the black hole. And we look at the exteriors of the black holes. And again, we think about what happens if the ADM mass is going to 0. It's becoming flatter and flatter. And in what sense does this converge to Euclidean space? There's a hole in the middle that doesn't, the topology has changed in this picture. Then in this example, also with black holes, but these are black holes that are down deep gravity wells, which could occur, for example, if a black hole has a lot of dust going around it, so that the space is actually curved in and almost straight here because of a dust field around the black hole, would be one way to picture that. So even though the well is getting deeper and deeper, we would like to consider in what sense it might converge to Euclidean space. And the same thing can happen just with gravity wells in general. You are, again, we're going to have the ADM mass going to zero, so there's less and less mass in here, but maybe it's a higher and higher density planet in the middle. And we would like to say, oh, in what sense does this also converge to Euclidean space? The only one where this is smooth convergence is here on the left. And these other ones are going to not work, in particular in the joint work with Dan Lee that has this image in it. We showed there are examples that are not smoothly, and they're not Gromov-Hausdorff. In fact, the Gromov-Hausdorff limit of this sequence here on the far right, this Gromov-Hausdorff limit would actually be a Euclidean ball with a line segment attached. And the length of line segment would depend on the depths of these wells, so you might need a subsequence to even converge. But we do propose that intrinsic flat would work, and we prove the intrinsic flat does actually work in this rotationally symmetric setting where it's a spherically symmetric picture like this, and there's only a warping in one direction. So what I want us to discuss at this workshop, we're going to focus on, so at this workshop, we're going to focus on progress and new approaches. And so what I want to do in this first talk is just sort of give some background of some of the older results and the status of some of the older results, what's happened since, and then I won't mention the results that are actually going to be presented at the workshop. So first, let me get into more detail. Asymptotically flat manifold. So the first example of an asymptotically flat manifold would be Euclidean space. Let's call this one Euclidean space. And the next example is the Riemannian Schwarzschild space of mass M. So this Riemannian Schwarzschild space here, I'm going to just try to draw it over here, MSCH of mass M. So this is the standard black hole. You think of it, this is one way of writing it. Take an R3 here, remove a hole at the center of the R3. So we just consider this. This is our manifold, which is an R3 with a hole removed. Let me remove the hole in black here. So we take out the center point here. So we've taken out this point, the origin, and we put the metric tensor on this manifold to be this formula here. So it is conformal to Euclidean space, and the mass is appearing right here in the formula. So now you get a sense of what the decay should be when we say that it has ADM mass is equal to M. It means it's sort of asymptotically similar to this Schwarzschild space of mass M, where M is just a constant in the formula. Now over here, there is this rho. So this rho is actually equal to the absolute value of X. So you'll notice that there is an asymptotically flat end as rho goes to infinity. This will be dominated by 1 plus, and this will be a decay, right? But notice also that rho equals absolute value of X going to 0 will also cause an asymptotically flat end, and you can do an inversion formula. Because of this division by 2 rho, we end up where as you approach origin, you're coming out as an asymptotically flat end again. So really, Schwarzschild space can also be drawn as a parabola rotated, where this is a sphere here. And this is another way of drawing M Schwarzschild of mass M, and the rate of decay of this parabola depends on M. And you'll notice when you draw it in this way that there is this minimal surface sigma at the neck. And actually this minimal surface is occurring, if I draw it in this place here, this is happening at absolute value of X equal to M over 2 when we describe it using the conformal metric tensor. And the area of the surface is exactly equal to 16 pi m squared. So this is Schwarzschild space, Riemannian Schwarzschild. There is also Lorentzian Schwarzschild, which includes Riemannian Schwarzschild as a slice in the space. Now, we had mentioned exterior regions, so I really want to emphasize them. The exterior region of Riemannian Schwarzschild will be the place where absolute value of x is actually bigger than m over 2. So now we're only considering the outside of the black hole here. And I'm going to use a prime to indicate that. And here, it's just the one end where here we're taking rho going to infinity. So it's the outside, the exterior. Now we have only one asymptotically flat end when rho is going to infinity, and it has this boundary m prime, which is equal to the minimal surface. And notice that in that case, the ADM mass of the Schwarzschild exterior, which is this m, that's in the formula here for its metric tensor, is also equal to square root of area of the boundary of m over 16 pi. And this is the exact formula depending on area that is then appears later in the inequality for mass. That mass will be bigger than or equal to the square root of area over 16 pi for other examples. All right, so that's one case. In the next slide, you'll see all this information plus a new piece, but the picture will go away. So now here, all this top here is the same as before. This is the same information I already gave you. And now we have this new example here. These are the Brill-Lindquist geometrostatic manifolds. And so these guys have many points removed. And that's why I wanted to write Riemannian Schwarzschild in this way. So now we're removing up to n points. And we're taking the metric tensor to be some conformal factor chi to the fourth power delta, where chi here is has got these little pieces of alpha I divided by, and now we have rho I. Now rho I is actually just equal to the pi minus x. So we're going to have lots of asymptotically flat ends. We're going to have them when the pi minus x goes to 0, and also when absolute value of x goes to infinity. So this is a space with a lot of holes. One at each of the pi's. You can find an outermost minimal surface. It does exist, and it might go around some of the pi's, but maybe if two of the points are really close. Brill-Lindquist did note that sometimes it might go around two of them at once. So the sigma that's outermost minimal, which I will give more precise definition of what outermost minimal means in the next slide. Then the exterior will be the region where this sigma here is the boundary of that region, and we're going to include the outside only. So think of it as outside the black holes, and we don't care what's happening inside the black holes. That would be m prime. And the mass will be this m, and in this case, the mass is supposed to be the asymptotic behavior as we go out towards absolute value of x towards infinity. So we're talking about the mass of the end at infinity. And for that mass, you'll see the alpha I add up to tell you the behavior at infinity. So you actually have to sum them. And so that mass will be bigger than 0 as absolute value x goes to infinity. All right, so that's another example with many black holes. So now let's talk about the rough idea of the key definitions here that we're going to be talking about. An asymptotically flat end is a region U contained in our manifold that's diffeomorphic. So again, we're sticking to 3 dimensions in this talk. So it's diffeomorphic to R3, removing a ball. So that's what an asymptotically flat end is. And G goes towards the Euclidean delta as absolute value of x goes to infinity up to some second order in some way, which Dan Lee can make more clear in the discussion afterwards if you wish. In particular, remember that the Schwarzschild space was becoming kind of asymptotically flat, going towards delta, but not so fast that the the decay will then depend on M. In fact, if G is going towards Schwarzschild space here, if the metric tensor starts looking like Schwarzschild's metric tensor of mass M as x goes to infinity, if you have this situation, then the ADM mass will be equal to M. Now, there's another way to see the formula for the ADM mass, and we'll see quite a few formulas for ADM mass. So various formulas for ADM mass. For ADM mass will happen this week. Will be given this week, and a big part of understanding the stability of this positive mass theorem is finding a new formula for ADM mass. Okay, so that's exciting that there have been some new formulas found in this past few years. So one simple way to define the ADM mass is you use the Hawking mass. The Hawking mass of a surface. So now this surface is not necessarily minimal, so I won't make it red, okay? So Hawking mass of a surface is the area of the surface. The area of the surface divided by 16 pi square rooted. You'll recognize that from the Schwarzschild mass at infinity. Times 1, so this is the actual decay, minus 1 over 16 pi times, this should just be sigma here, times this is the mean curvature, h squared d sigma. A closed minimal surface is one where the mean curvature h equals 0, so I'll use red for the minimal surfaces. And we say that sigma is actually an outermost minimal surface for you okay, so here let me draw a picture where it won't be outermost. So let's just draw a picture with a few bumps here. In this picture here, you would have a minimal surface here, a minimal surface here, a minimal surface here, a minimal surface here. The outermost one is the one that's closest to the end. So this is the outermost one. And to be more precise, it's outermost minimal surface for the end, which I'm labeling with the set U. If for every region that contains U, such that the boundary of the region is minimal, we have sigma inside that boundary of the region. So the outermost one, other omegas in this picture might be ones that reach all the way down to here, and they contain that outermost sigma is the one that all of them are contained in. There are various different ways to do it, so I just want to let you, that's one way to write it down. So the outermost one is the one closest out there. There's no reason that this outermost minimal surface would be connected. So you could have a space with 3 ends, which happens, for example, with Brill-Lindquist with 2 points. You could have a picture like this, and it's possible that the outermost minimal surface is broken into 2, one about each of the points. So it doesn't have to be connected. And then the exterior region, this exterior region, M prime is the part that's contained above sigma, but the definition of exterior depends on which end you're talking about. So the end as absolute value of x goes to infinity would be perhaps that one. But if I had chosen a different end, if this was the end I was interested in, then this would be the exterior region. So the exterior region is depending on what you chose to be the end you're interested in studying. Okay, so Huisken, Ilmanen, and Bray proved the Penrose inequality. And they studied exterior regions as above, satisfying the Penrose inequality. They studied exterior regions as above, and they proved that they satisfy the Penrose inequality. So the mass, which we write as M-ADM, of the exterior region, M prime, is greater or equal to this formula involving the area of the boundary of M prime. And it's very much required that this boundary actually be outermost minimizing, because you can see anything can happen below this. So this one is not outermost minimizing. And that one could in fact be very large, have large area, arbitrarily large area. So the ADM mass is only controlled by the outermost minimizing one. And afterwards, once you get inside, you can make a very, very large bubble inside with an arbitrarily large equator. So the way their proof proceeded, this is the Huisken-Illmanen proof. There's a generalized, so this is Huisken-Illmanen's, not Brace. So there's a generalized inverse mean curvature flow of surfaces sigma r starting at this outermost minimizing boundary. And so these, they flow forward and then they connect at some point, and then they keep flowing out, and they become these round things at some point, very round as you go into the asymptotically flat region. And the Hawking mass is increasing as you go through these levels. This is a generalized inverse mean curvature flow, so they're not necessarily smooth level sets. And the Hawking mass starts at the beginning where, well, H is 0 at the beginning, so it's just this formula, which is the formula for the Penrose inequality. And then they increase, and the limit as R goes to, this should say infinity. Wow, that's a big typo. R goes to infinity of the Hawking mass approaches the ADM mass. So that's a one definition for ADM mass, is that it's the limit of the Hawking masses of round spheres of increasing radii in the asymptotically flat region. The rigidity case is if the only way this would actually be equal, where there's equality throughout this entire proof, would be that there's not actually increasing, but that the Hawking mass is staying constant for this entire process. And then in that case, the Hawking mass is constant, mh sigma r equals a constant, and you end up that the exterior region of M prime has to be Schwarzschild space. That is the only space where the Hawking mass is constant as you go through the inverse mean curvature flow. All right, so this is all the terms that we needed to sort of make everything rigorous. Any questions? Okay, confirm that you all hear me. Yes? Okay.
Yes.
Good. Okay. All right, so now we continue. The rotationally symmetric case, that was scalar gradient with the 0. Now in this case, we will describe our G with a ds squared. I'm not necessarily using the same letters as this is joint work with Dan Lee. But also there's Gauche monotonicity, which is by Gauche, of course. So now in this case, we have all these spheres. So each of these levels is a sphere, and we're calling them sigma r. And these spheres go through the Gauche monotonicity. The Hawking mass will be increasing for these spheres. Notice that these spheres will be minimal surfaces only when they are actually critical points of the function fr. So we have lots of minimal surfaces in this picture. So these are the minimal sigma r, which happen when f prime of r equals 0. And then this sigma r naught at the top here is outermost minimal. And then if you take your inverse mean curvature flow from here, it will go nice and smoothly and actually stay in these spheres with the symmetry, and you'll have Gauche monotonicity that the Hawking mass is increasing, starting again from this area here for the sigma naught. That's the exterior, the outermost minimal guy, or sigma r naught in this case. And you get that's equal to the area sigma r naught over 16 pi, and then it increases to the limit as r goes to infinity of the Hawking mass, which gives you, this is r going to infinity. You get to the ADM mass. So again, we have, of course, the Penrose inequality satisfied very simply in this case. If for some reason the manifold doesn't have an outward minimizing surface, so in this case, we're going to have no boundary, and then we assume no minimal surfaces, no min surfaces. And in this case, you can also do the inverse mean curvature flow, just starting at a point, there is an inverse mean curvature flow. So we still have an IMCF, inverse mean curvature flow. And as long as it's smooth, any manifold with a smooth inverse mean curvature flow has Gauge monotonicity. So these are the sigma r's, and the Hawking mass increases, non-decreasing, okay, up to ADM. All right, so we have the situation. So I shouldn't actually say this is joint work with Dan Lee yet. The joint work is what when we consider on the next page, over here. So that's where the joint work comes up. So far, what I talked about was Gauge. So let M3G, where G is of this form that we just talked about, we have this Gauge monotonicity. I just already talked about this. And then these examples are in my paper with Dan Lee, where we looked at the various examples and we constructed specific examples, and we showed that so some of them have the outward minimizing minimal surface and some of them don't, and we discussed the convergences as the ADM mass goes to 0. So in this direction, we're taking sequences of MJ, and that the ADM mass of MJ is going to 0 as we proceed downwards. And this is the limit space of infinity, which is actually just Euclidean for each of these. Okay, so what we do is we fix an A naught and an R, and we take PJs that are on sigma SJ. So the PJs I've drawn here are these points. And what I've done is I've put them on level sets of fixed area. So these level sets have fixed area, A naught. I'm assuming that they're lying on these spherically symmetric level sets of fixed area. And if we choose those base points, then we will get a limit as a pointed limit as the ADM mass goes to 0. And the region that runs from SJ minus R to SJ plus R, so this whole part, let me use another color. So we're going to stay in the exterior. So the exterior, I've only drawn the exteriors here. So these are all MJ primes. But what we're going to focus on is these regions from negative R to R. So let's just make this green. So we focus on regions like this around this level set. Now, if R is big enough, we'll reach the bottom, and that's great. But we won't always reach the bottom because it's possible these can get arbitrarily long. So this can get deep to infinity, and so can these. But what we show is that these regions of omega J's that don't get too deep, they only get as far as SJ minus R. So we're only going to go down a distance R. But for all R, we are allowed to go down a distance R, and we will get a limit that will be a region inside Euclidean space. That's an annular region, or if the R is big enough, it will be a disk inside Euclidean space. So this is, and then as a consequence, we'll get pointed intrinsic flat stability. So we do not, however, get smooth Lipschitz or Gromov-Hausdorff stability. As I mentioned before, the limits would be Euclidean space with intervals attached in the Gromov-Hausdorff case. But we might need a subsequence to handle different lengths of intervals. So this is why we are focusing on intrinsic flat stability. All right, so this is a fairly old results. I'm going to try to move along a little faster. The definition of intrinsic flat distance. What is this actual definition? I think everyone here knows this definition. The intrinsic flat distance between two manifolds is the infimum if you embed both of the manifolds into a common space, and you look at their flat distance inside the common space Z. So the common space, we put them both into the same space. Z is any complete metric space. When we put them in, we only use distance preserving maps. So the phi i's are distance preserving from MI into Z. Both manifolds have to be the same dimension, and then we estimate the flat distance between them is less than or equal to a volume of an A. So after they're sitting inside Z, say one of them might look like Euclidean space, and one of them might have a well. And after they're inside Z, we want to measure them with this Federer-Fleming flat distance. So that means we will close up a boundary here, and we will have a solid inside. And we'll say that the flat distance between them will be less than the filling, this way we filled it in, and the interior, that's one dimension higher. Okay, so I'll have a better picture soon. The idea is that we can actually use things that are more general than submanifolds, but the main idea is that we need that phi1 of M minus phi2 of M is equal to A plus boundary B, in the sense that when they act on differential forms of the correct dimension, they integrate in this way. So they're defined by Stokes' theorem. That's what we mean by saying that we close it up with B, so that we close it up with A, so that the boundary of B, this boundary of B will be A, and this part and this part sitting inside Z. The explicit constructions of this sort to actually estimate intrinsic flat distances are completed in my joint work with Stefan Wenger, where this intrinsic flat distance is defined, this original paper here, and also in the paper I did with Dan Lee, which was soon after this one, where we talk about ADMS. So let me just give a little more information about this. There is this nice lemma in my joint paper with Sajjad Lakhsian, which allows you not to worry about that complicated definition. So the advantage of this one is it says that if you have two manifolds, so assume that one of them is like Euclidean space here, I've drawn it here. So suppose my M1 is Euclidean space, and then suppose your other M is one of these spaces with these wells that we've been talking about. So maybe this one has a black hole here and a well over here, and it's asymptotically flat. So that's my M2. And suppose you want to estimate these two guys, and you don't want to know a lot of things about embedding in symmetric spaces and all of that. If you don't want to worry about that, you can just use this lemma. And the lemma says that all you have to do is find regions inside each MI. And these regions inside MI, let me use the right colors here. I think I was going to use purple for this. So these regions UI inside MI are going to be regions where they look very similar in a smooth way. So this big region here away from the pink and this region are close, are smoothly close. And if these regions are smoothly close, and then we take out these regions that are not close. So a long skinny region is not close to something inside. This region and this one are not close to anything inside Euclidean space. So what we do is we cut those regions out. So that's these MI take away UIs. And what we can do is we can estimate the flat distance. It's only going to depend on the volume of the M's take away UI. So we estimate the volume inside them, inside where we cut. So it would involve these 4 volumes. It will also depend on the boundaries. And then the part where they're close. This part where they're close. And this C is a length, which is going to depend explicitly on how close they are on the UI. So as long as the G1 and the G2 are similar to each other on the UIs, this is almost flat. I mean, I know I didn't draw it so, but this is somewhat smoothly close away from the pink parts. So this is a very useful lemma that has been used by a number of people to estimate the intrinsic flat distance. Here's the proof of that, which I'm going to skip, but you can look at it later. This proves it by actually explicitly embedding it into a Z and showing why we can estimate something a 1 dimension higher. I'm going to skip this. And then we get to applying this. So that lemma was applied in my joint work with Eva Stavrov. So we studied the geometrostatic M3. So this is with Eva Stavrov. And we looked at these Brill-Lindquist geometrostatic manifolds. It was known already by Brill and Lindquist and others in the 40s that M80M of these guys is equal to the sum of the AIs. That's easy to check. And so then the process is you take one of them, and we've removed some points. So I've removed P1, say this is P2 and P3. And then the next step is, okay, what does that really look like? Well, if they're spaced far enough apart, the manifold actually really looks like this, with these asymptotically flat ends corresponding to each point. So each pi gives an asymptotically flat end. So that's my M3. But actually, what you want to know is you want to know where M prime 3 is. Sorry. Let's just call this M and not put the 3 on it so I can write M prime. So M prime is just the exterior. We want to know just the exterior part. So what we have to do is we have to find sigma. So this is really the hard part of my work with Stavrov, is we find these sigmas and we actually show under what circumstances they end up disjoint, one separate one for each of the PIs, which really lets us then say exactly what the exterior region is. And then we're able to go back to the original, and we're able to say, okay, this is my M prime. We have this exterior region and we have these minimal surfaces. And it's this M prime we want to show the ADM mass getting small is that M prime is supposed to approach Euclidean disk. So the first thing, so this is pretty much saying the same thing that we have here at the very top. And we notice that this point, if M is small, then all the alpha i's will be small. So we'll definitely have that this chi x here, that guy is going to be close to 1. But not near these places where the rho i's go to 0, because that will be an infinite. So we'll only have it small away from the PIs. However, wherever chi goes to infinity, we'll have these guys are actually going. Okay, so it's small away from the PIs, but when we're near the PIs, it actually is going all the way to infinity. So what we do is with EVA, we fix some sigma and we assume that the points are at least sigma apart. So we're assuming that the PI and the PJ are definite amount apart. And then we say, okay, let's see, we don't fix where the PIs are located, but we say when the mass is small, the outermost minimal surface, where is it? So we're able to estimate exactly the location. So if this is my PI, okay, right here, we don't know the exact shape of our sigma i's. They can be quite bad. Brill-Lindquist did some numerics to say how bad they were. But what we are able to do is show that they lie in an annular region between an RI and a capital RI. And this way we're able to locate the minimal surfaces inside these annuli. So each sigma I, part of the exterior minimal, lies in an annulus about its PI. So we actually locate these more precisely. In the next slide, I show you a picture where we've done this. So here's the picture. I'll just make it large for a second here. You see each one of these minimal surfaces is located inside these annuli. And so the next thing we have to do is we want to apply the estimates. So this says all the same things as the last slide, okay? And here's the picture now. I added the annuli to the picture that we had before. And here's what we said about how each one of these sigma I lies in an annulus. And here is the 2 radii. And the first radius is only going to depend on the alpha I of that particular point. That's the inner radius. And the outer radius is going to depend on the area of its minimal surface. But this area of this minimal surface will be bounded using the Poincare inequality. So when mass is going to 0, this is going to be small, and so will the Ri. But we'll know exactly how these are behaved in a kind of uniform way. We do need to assume the points are definite distance apart to get this. And on the exterior region M prime, we then show that at chi x, which is the conformal factor here, is close to 1 away from the region of small volume. So we actually show it's close to 1 outside of the annuli. And then we use Lexion Sormani to show that we have the volumes are small elsewhere. So let's just emphasize this point that our region where we have almost diffeomorphism is outside of the annuli, and then we control the volumes between the outer part of the annuli and the minimal surface here by actually just controlling the volumes of this entire annulus. And then we also have a control on the areas of these minimal surfaces, and that's using the Poincare inequality. So we're then able to show that the intrinsic flat distance for large balls inside the geometrostatic manifold and a large ball inside Euclidean space, the intrinsic flat distance is small between these two balls. So it's close to Euclidean space in that sense. All right, I'm going over, and I'm just gonna be very quick. I only have, I obviously prepared way too long to talk. Okay, so stability of the positive mass theorem. In other cases, there was earlier work with by Finster, with Bray, and with Kath, by Corvino, by Dan Lee. They didn't deal really so much with the interior wells. Then there's a rotation symmetric case I talked about with Lee. The key idea was to use intrinsic flat convergence to handle the wells. The regions with smooth inverse mean curvature flow have also been studied by Brian Allen. He's here. Warning, Huisken and Illman and inverse mean curvature flow jumps over regions. But Huisken has suggested bounding the volume of the jumped regions, perhaps using his isoparametric mass. Jorgway and Jorgway Lee have worked concerning volume preserving intrinsic flat convergence and Huisken's isoparametric mass, but they haven't done this thing that Huisken has suggested. But they have some very nice results in other respects. Stability of regions in axisymmetric manifolds. So axisymmetric are like cylindrically symmetric. These have been studied by Edward Bryden. Don't have intrinsic flat estimates yet, but have W1P kind of estimates on the metric tensors. And others are presenting the stability results this week. So here I was trying to get at the point of how to get to intrinsic flat stability and what to do if you don't know where the minimal surfaces are. So I'm just going to keep going a little longer because I did prepare more. There's other ways to find, to prove intrinsic flat stability. So all I showed you so far was construct explicit estimates, or to use the paper with Lexion where you have a smooth region and a region of small volume. But there's also volume above, distance below approach, which is in joint work with Allen and Perales. Of a compact manifold N without boundary, if the GJs are greater than G naught, and if the volumes approach this and the diameters are uniformly bounded, you get intrinsic flat convergence. So we have this paper, and I don't have time to talk about what they do exactly, but they have this same thing for regions with boundary, which are the ones that are useful in this setting. They have various hypotheses on the boundary that I don't have time to present, but the idea is here would be your manifolds that are approaching Euclidean space. So you would want to show there's distance decreasing map to Euclidean space. And then you want to show that the volume converges to Euclidean space. So if you can do that and you can control the boundaries the right way, then you can use VADB for regions with boundary in order to get intrinsic flat convergence. So this is actually very weak, what you have to show, only just volumes and the metric tensor bounded below. So this is a strong theorem here. And the boundary version is what you want to use for the ADM mass. All right, so one setting where this was actually applied is for the positive mass theorem for graph manifolds. If MJ lies graphs above Euclidean space, then they have this GJ greater than or equal to G setting. They already have this picture. They are a graph. They are a graph above a Euclidean space. So they're already graphs. So then, okay, they will have the GJ greater than or equal to the delta of Euclidean space. And Huang and Lee showed that their mass is going to zero. Certain volumes can be controlled. And then Allen and Perales applied their VADB with boundary. And their estimates will show regions in such MJ without boundary as the ADM mass goes to zero, convergent intrinsic flat sensitive balls in Euclidean space. So they're applying this technique. But they didn't deal with, they only dealt with wells and not with possible black holes that could also occur in the graph case. So for the graph case, Huang, Lee, and Perales handled the possibility of having outward minimizing boundaries as well. So they also using the VAD method, but they have to be they have to do extra work capping off sort of these things, so that they can then have a reduction to the case where there is no boundary, and it actually is a map from here to here with GJs and G's delta. Okay, note that they do not need to know where the boundaries are located. They just say if there is a boundary, it has certain properties, and we can do this. So it's very important that you don't know where your black holes are. You can still show you have convergence to Euclidean space. So far, I talked about techniques for proving the intrinsic flexibility. I just summarized them here. There's the explicit construction method, and here's places where this was done. Also in joint work with Sakovich, we did this. There's using volume estimates in diffeomorphic subregions, which is the theorem is in the work with Lexian, and the example of using it is in the work with Eva Stavrov. Using volume above, distance below, this is work of Alan Perales and I, that to do the original volume above, distance below, this is the one with the boundary. This is when Huang and Lee Perales handle the possibility of exterior minimal surfaces. Sorry, outward minimizing minimal surfaces. And there's also work of Cabrera Pacheco, Graf, and Perales, which is the asymptotically hyperbolic case using this VADB method. There's also work I forgot to mention here with Sakovich, where we also do asymptotically hyperbolic, but we use the volume estimates and diffeomorphic subgroups. No, it's here. We use this one. I'm sorry, I'm getting a little rushed. Okay, we actually use the explicit estimates for that one. So now applying the flat compactness theorem, this is a new approach. I just want to talk about this one because I think this is one of the cooler approaches. So I am continuing to run over on purpose. Okay, you can apply the intrinsic flat compactness theorem. There's one proven by Wenger and there's one proven by Lang and Wenger together. And then proving a limit space must be Euclidean space. So and as a flat compactness theorem says, you have a sequence of manifolds, a subsequence has to converge to something, some sort of limit space, and then after you get the limit space, you show it's Euclidean. So that approach was used by Huang Li and I in our original paper, but we had a gap. So to fill in the gap, we can use Delnine and Perales fill in the gap. So I wanted to talk about this a little bit because some of you may have heard there was a gap, and now I wanted to just tell you that Delnine and Perales have that filled in. So what does it mean to apply a flat compactness theorem? First of all, just to emphasize the point, when we first defined intrinsic flat convergence, we defined it for integral current spaces, not just manifolds. And these are oriented, countably rectifiable metric spaces. So they have countably many charts that are by Lipschitz. That's what this means. Countably many by Lipschitz charts. Also, they have a notion of boundary, and their boundaries also have countably many by Lipschitz charts, and they are oriented, meaning the charts have an orientation on them, not just orientable. And we prove that whenever you have intrinsic flat convergence, you also have the boundaries converging, and that the volumes of the limit is less than or equal to the limit for the volumes. And all of this work uses Ambrosio-Kirchheim theory. So then Wenger proved his compactness theorem. So that's why we have this compactness theorem right here. That if the volumes are bounded above, the areas bound of the boundaries are bounded above, and the diameters are bounded above uniformly, then there's a subsequence which actually has some sort of limit. So we get this limit space n infinity, and the n infinity space might be 0 if everything disappeared or canceled in some way. And then so there's also a theorem that I have in my Arzello-Scoli paper that says, okay, if you have functions from the sequence to a compact metric space, and the Lipschitz constants of these functions are uniformly bounded, and K is a compact metric space, then there's a subsequent, and the domains converge in the intrinsic flat sense, then there is a limit for subsequence. There's an F infinity that's Lipschitz going from the limit space to K. So this is an Arzello-Scoli kind of theorem. There's a few in this paper, but this is the one that I'm going to talk about. And then Delnine and Perales have actually shown even more properties of n infinity. And there are more people recently showing more and more properties of these integral current spaces. They are quite, take a lot of geometric measure theory to understand their properties. But the idea is that you can use your technique even if you don't know geometric measure theory as long as you can get the kinds of controls that are needed in order to apply the results. So how do you apply this to graph manifolds? I'm going to just slide up now, but the whole top of the next slide is exactly the same as this. So all of this is what I just talked about. So in my paper with Huang and Lee, we were considering graph manifolds. So we had these manifolds that were sitting as graphs above Euclidean space. And then we said, oh, assume they're uniformly flat at some level R. And so we made that like they were by Lipschitz on this boundary. And we had a depth bound so they didn't get too deep, and various technical assumptions. And so one can think of this as, oh, there's a map, Fj, that's going from our manifolds. This is the manifold viewed as itself, as an intrinsic Riemannian manifold. And here it is placed by an Fj into the space. And now we're going to use all these strips. And what we did was get this far, but we needed more that Delnine and Perales have filled in. So now I'm just going to switch to a slide that has all this information at the top here. But I move my picture over here, okay? So what we're going to do is we had gotten this far in the discussion and we're up to here. So the idea is that we want to use the Wenger compactness to get a limit of the of all our smooth guys. So we prove volume and area bounds, and we have the depth assumption, so we get the diameter bound. And so Wenger gives us that there is this limit Riemannian manifold with boundary, but it's not a Riemannian manifold, it's just rectifiable. So I drew it with lots of bumps, okay? So it's got these by Lipschitz charts and stuff. It's this rectifiable guy. And then, oh, well, it was a graph, so the Lipschitz Fj was less than or equal to 1. So actually we have this F infinity that maps it into the Euclidean space. So we have this guy too. So we have this rectifiable guy mapping into here. And F infinity was by Lipschitz on the boundary. So actually it wraps around still R. So this boundary here is wrapping around this cylinder. And now if this was a smooth manifold and it had boundary, and we knew that it wrapped around the cylinder, and we also know that the volume of this guy here, this volume is equal to the volume of the ball down here. If you have a smooth manifold and it's wrapping around the cylinder and its volume is as small as this Euclidean ball, it has to be the Euclidean ball. There's no way for it to be anything but the Euclidean ball. And so Huang Li and I had written that therefore it was Euclidean ball. But actually one needed to understand integral current spaces better in order to really actually justify this last step. And so that's what Delnine and Perales have done. They've really justified what it means when you say wrapping around and that it becomes flat Euclidean ball. Okay, so even when it's not a smooth manifold, it's rectifiable. So they use, Ambrosio-Kirchheim theory to make this all rigorous. All right, so that I wanted to let everyone know about. So now the original proof, if you attach Delnine Perales' work here, which really makes people understand integral current spaces better, then you can do this method of using a flat compactness. All right, and then here I had the final slide, and it said why people want to prove intrinsic flat stability. So there are all these consequences papers that say what you get after you've proven intrinsic flat convergence. And there are also consequences if you assume it's volume preserving, which means the volumes converge and you have intrinsic flat. So the semi-continuity of eigenvalues, semi-continuity of mass, relation to capacity that will be presented this week. And there's additional problems related to flat convergence and scalar curvature in Gromov's work and in the survey of the IAS meeting from a few years ago. So, and here's the website with all the papers. Thank you very much. Sorry, that was such a rush. I'll put the slides up.
Thank you very much. I think we're so I would like to open up for questions and then also pass the baton to Dan Lee, because I think he's taking over the moderating, but
yeah,
or did I surprise you with that? I hope not.
No, that's right.
Okay.
So what questions do people have?
I went way too fast.
So I don't know if I didn't catch it. When you're talking about the geometrostatic theorem, so do you in that paper, do you have to deal with I guess when the points get very close, there could be a horizon surrounding 2 points, not just the single
Yes,
one?
it's known that there are horizons surrounding 2 points, so our theorem only concerns the case where we fix them apart.
Uh-huh.
So
I
the
see.
case where a horizon might surround 2 points is an open question.
Because okay, so you're fixing the sigma.
We have a fixed sigma at the beginning, which we don't fix where the points are located, we fix a sigma. And as long as the points are at least a sigma apart and then take mass to 0, we have these annuli that are shaped like this.
Mhm.
Brill and Lindquist did numerics.
Right, right.
And showed examples where, rigorous kind of numerics. Definitely are cases where the minimal surface goes around 2 or more and has very strange shapes. And by rigorous numerics, I mean the kind where they know how close that the minimal surface is to their actual projected, finite element method, as they know exactly that the minimal surface definitely is going around the 2 points as a consequence. Yeah, so this is a nice setting. I should mention that Stavroff has a number of additional papers with students about geometrostatics. Many geometrostatic papers. Other results not related to PMT. Like what happens if you have many of them and they're ordered in a nice way and they become more and more dense. So she has looked at the other cases, but not in terms of mass going to 0. Unless she's done it more recently.
Can you comment on what you might need to do if you want to do something more general? In the case where you
So the
allow
concern, the method we used, if it had so the picture, the geometric intuitive picture of something that might include 2 n's is if it looks like this. And what would happen is that there would be a minimal surface here, and there would be these guys. This would be the outward, right?
Mhm.
Min guy. There would be 2 others. And our R alpha I is going to capture the R alpha. So the R alpha I is going to be all the way out here, and the capital R is going to be up here. So we don't know that this will be a small. So this would be like an R1 and